I'm Daniel, and I worked in Professor Scherer's Caltech Nanofabrication Group this summer, and I'll be presenting my research on this device, metal vacuum metal tunnel junction, and this is a device made via Angle Deposition. So first, let's begin by talking about silicon devices and silicon transistors. This is a silicon-based MOSFET, and it's the foundation for basically all of the electronics that we have in our modern world. The development of silicon devices have been described by Moore's law for decades, which states that transistor densities double every 2 years. And so society at large has invested a lot into silicon electronics and its growth, but now there are significant technological hurdles which stand in the continued shrinking of silicon devices. So on the left here, you see a few. When you get down to very low dimensions, even modest voltages will cause extremely high electric fields, and that can start causing breakdown in materials. At such small dimensions, you also have higher carrier leakage currents, and impurity doping, which is the method that's used to make these silicon devices, having P-type silicon, N-type silicon from doping, also breaks down at tiny scales, because if you only have so many silicon atoms, even extremely high dopant concentrations won't work at such a low volume. The alternative that the Caltech Nanofabrication Group has looked into is vacuum devices. And vacuum devices have a few advantages. They can sustain higher temperatures because they are no longer relying on the properties of silicon. And the electrons themselves can travel at higher speeds. There's a limit of about 100 kilometers per second in silicon, which sounds high, but at super high speeds it does become limiting. But in vacuum, it's just the speed of light. So as Professor Scherer would say, nothing is better than silicon. Vacuum itself is a better foundation for devices than silicon. So my specific project looks at vacuum metal tunnel junctions. And so we should talk a bit about quantum tunneling, the quantum tunneling of electrons. At the top is a simplistic diagram. An electron which quantum tunnels through doesn't have to increase its potential energy and go up the classical hill. And the bottom is a representation in terms of quantum wave functions. We see that if there's a potential barrier, as long as it's thin enough, it's possible for electrons to tunnel through without needing too much energy. And this is a principle that's tried and tested. Here are two diagrams of scanning tunneling microscopy, which is where a very sharp tip lies about a nanometer above the surface of a sample. And it moves around, and by passing a current through it, whose electrons are quantum tunneling, you can move the tip around and find the geometry of the sample. So this is a principle that's very much tested. And here's some past experimentation from Professor Scherer's Nanofabrication Group. On the left is a device with 4 electrodes, and on the right is a simulation of the electric field of this device. The left is an electron microscope image. And when you apply a voltage to the 2 side electrodes, you can see that an electric field is developed. And the 3rd and 4th electrodes at the side are intended to modulate the flow of this current. Lastly, here is an image of a traditional metal insulator metal tunnel junction. And the issue with this is that it's very difficult to add additional electrodes to control the electron flow. That's why we are going for this geometry with my project. We have a base of ytterbium fluoride, which I'll get into later, but there's a trench in the material, and metal grows from the corner of the trench. And this gap is the gap between the 2 pieces of metal through which the electrons tunnel. And I say metal vacuum metal tunnel junction. It's not the case that this device has to be put in a vacuum chamber to work. It's just that this gap is so small that even at atmospheric pressures, on average, there will be 0 air molecules in that. So I can now describe my intended approach. To begin with, we do still start with silicon, not because we need its semiconductor properties, but just because it's the nicest, flattest material. And on top of that, we deposit a few hundred nanometers of ytterbium fluoride. And we do this with physical vapor deposition in a setup that looks something like this. And then we create this trench. Now, there are 2 main reasons we chose ytterbium fluoride. One is it's an ionic material, so it has very high resistivity, and so it won't mess up with the electrical characteristics. But also, very interestingly, it's a self-developing electron beam resist, meaning if you hit it with an electron beam, the material itself will essentially evaporate or disappear, leaving behind a trench. So we hit it with an electron beam using this, a scanning transmission electron microscope. Here's the image of the specific microscope we use, and in here an electron beam comes down and hits the sample, and these coils guide this precise position of the electron beam. And the specific way in which ytterbium fluoride develops isn't fully understood yet, but here are two possible hypotheses. One is that bubbles form, which then coalesce and form a channel like this. Another is that the channel itself grows from the top to the bottom. We're still not certain which exact way it is, but we do know from experimentation that ytterbium fluoride does get developed by an electron beam. So we have that trench, and now we cover everything at the top with a layer of PMMA, which is a polymer, and it's a very conventional electron beam resist. And we create that very thin layer of 200 nanometers or so by using a spin coating machine like this. We place the sample right here and put liquid PMMA on the top, and by spinning it extremely quickly, we can create such a thin layer. Once we have that layer of PMMA, we then use a device like this, a scanning electron microscope, so slightly less complex than a scanning transmission electron microscope. And this electron beam can also be scanned along the top of the sample, and we create exactly the trench that we need, which is sideways to the main ytterbium fluoride trench. With the PMMA orthogonal trench there, we can then deposit metal at an angle on the top. So this is also via physical vapor deposition, which means that the metal itself gets evaporated in a vacuum chamber. And because it's a vacuum chamber and they have the kinetic energy, they essentially just travel in a straight line. So they come in a straight line from this direction and begin growing from this corner of the trench. And so they naturally grow in this shape, and by stopping the deposition at just the right time, we can ensure a 1 to 2 nanometer gap here. So the rate of the deposition and the timing of the deposition matters a lot in terms of achieving that gap that we need for tunneling. Lastly, this additional metal on top of the PMMA is not needed, so a lift-off step is used to remove that, and we are left with the device that we want. However, all of this is still at a nanometer scale, and it's very difficult to create electrical measurements. So here's the overall summary step by step. And at the end, what we have to do is measure the electrical characteristics. Here is a voltage current plot, an IV characteristic plot. And it is showing the expected voltage current characteristic of devices with different separations between the two electrodes. So this is 2.7 nanometers, 2 nanometers, 1.2 nanometers. We can see that at higher separations, the electrons need to overcome the work function of the metal, and so this is field emission. But once you get to a low enough separation, the electrons can directly quantum tunnel through, and so at any given voltage, you have a much higher current. And this linear VI characteristic is what we'd expect of quantum tunneling. We can see that at the equation here as well. Here's the voltage, here's the current, and there's a linear factor relating the two of them. So that is the criterion for success. We should manufacture such a device and attempt to measure a linear voltage current characteristic. And the probing would be through a station like this. So on to my specific findings from this summer. I wasn't able to carry through the entire process and make a complete device, but on the way of pursuing that goal, I did arrive at quite a few useful experimental conclusions. So the very first thing I did was work on step 3, that's the PMMA electron beam topography. It's sort of the most foundational basic step of this process. And to spoil the story a bit, here were my end results. You can see I did get, this is a test pattern, and you can see I did successfully write the test pattern on the surface of silicon. Any dark area is a layer of silicon coated by PMMA that has not been removed and developed. And any light area is an area where the PMMA has been exposed by the electron beam and subsequently removed. And you can see that down here by this 100 nanometer scale bar, I achieved a line width of about 100 nanometers. But this Certainly, I didn't achieve this first try, and I encountered a problem that looked something like this. So these were what earlier attempts looked like. And you can see that there's this sort of double image with spots all over the place. I tried other patterns as well. Here's a solid region, but you get the same weird noise. Here's a map of the US. These are supposed to be clean border lines, but again, you see the dots. I tried increasing the dose, decreasing the dose, all sorts of other things. It seemed like there was this persistent double image. But then it was this image that really gave us a clue of what was likely causing this problem. And I can show a rough animation of what it was like. So here's what's supposed to happen. The black dot shows the desired position of the electron beam, and it goes around and exposes the surface of the PMMA and draws the pattern that we want. However, there was likely noise introduced into the position signal of the electron beam because the position was actually encoded by just an analog voltage. So there was likely noise causing a digital jump like that. And when you add that to the position signal of the beam, you get a dot that moves around sideways like that. And if you then trace the path created by that beam with noise, you get exactly the pattern that we were observing. And this noise appears to be a certain digital jump with a fixed frequency. So since the frequency of the noise is fixed, as you vary the speed of the beam, the resulting pattern should also change. So here's a slower beam and we can see smaller dots. So going back to this image, that's exactly what we see. This is a faster beam with longer dashes. This is a slower beam with shorter dashes. And by realizing that that was the cause, we could calculate that the noise was roughly 240 hertz. And that was very useful in tracking down the final issue, which was indeed an equipment issue. It turned out that this specific monitor connected to the setup was causing interference, and simply unplugging the monitor fixed everything. Issues like this, you never know what causes them. So with the working setup, I then proceeded to optimizing parameters for PMMA electron beam lithography, and these were the parameters I ended up with. With that working, I then moved on to the next step of trying to make some good contact patterns. So here is, again, an image of the contact pad under an optical microscope being probed by two electrical contacts. Here's an electron microscope image. You can see it's roughly 0.1 millimeters. And zooming in to the very middle, and now at the 1 micrometer scale, we see that the tips of the two contacts aren't aligned with this line. And this line is the line on which our final MVM device will be made. So it's necessary that this makes contact with the rest of the pads so that electrical connections can be made. And the reason for this misalignment was because I wrote the line in the middle at a different beam current as the main contact pads. So in the future, when I make a contact pattern like this again, I should either choose a unified beam current or to create flatter sides of the contact pads so that there is some leeway with misalignment. Lastly, I assisted Professor Scherer with more fundamental research into the properties of ytterbium fluoride as a self-developing resist. Here is one test done where we just expose many different spots on the surface of ytterbium fluoride. This is a transmission electron microscope image, and on a very thin layer. We can see that as the dose of the electron beam increases, as you hit it with more charge, that the pixel intensity increases in that the amount of ytterbium fluoride which has been removed increases. Here's another related test, this time with lines, and as the line dose increases, in this case we actually see that the pixel intensity remains the same. And this is likely because even at the very lowest dose, the entire layer of ytterbium fluoride was already being completely developed in this case. So any additional dose was simply allowing the electron beam to travel straight through. So we also gathered some data onto this, data on the properties of ytterbium fluoride. Now to summarize my work, we were able to deposit ytterbium fluoride successfully, investigate the trenches, PMMA lithography went fine, and I was able to investigate some contact pad designs. But really, the step 4 and step 5 requires further work. I wasn't able to do any angle deposition, and I didn't attempt any sorts of lifting. So any future work would be focused on those. I would like to thank Anne Destabelle and her late husband Ray Destabelle for contributing the funds to support my project. And I want to thank my mentor, Professor Axel Scherer, and graduate students Richard Smith and Geraldine for guiding me throughout this project. Thank you.
Questions?
What was the reason for the choice of having 200 nanometers of ytterbium fluoride and the 100-meter trench versus even having a full trench? If you don't know how deep
so
it is.
those aren't, they're just order of magnitude numbers. The specific numbers aren't really determined by these diagrams, and these are things that really require experimental findings. So this is really just to give a sense of order of magnitude, not as a specific parameter.
How long does it take to create one of those spokes?
To spoke? Oh, about 1 or 2 seconds.
Oh.
Because the beam, those wheels are 10 micrometers in diameter. So the beam just has to scan across that. And it depends on your electron beam dose. So it depends on your beam current and the dose you want to achieve. With a higher current, you can do things quicker, but usually less precise.
Hi, so what is the major advantage of your technology compared with like standard lithography, like wrapping patterns?
So we didn't choose electron beam lithography because so electron beam lithography is better in that you can create smaller features because photolithography is limited by the wavelength of light. The other main advantage is with photolithography, you have to make a mask for everything you make, and we are doing experimental research, we're not doing mass manufacturing. So if we wanted to do photolithography, we'd have to make a mask first, and that requires electron beam lithography. And ytterbium fluoride itself is a good material, and we also wanted this project to be a chance to investigate ytterbium fluoride as an electron beam resist. So we basically just had the better equipment for electron beam lithography.
For step 4, the angle deposition, do you reliably get that 1 to 2 nanometer gap each time, or is there a failure rate associated with this?
No, we never really investigated that step throughout the process because the troubleshooting of the electron beam lithography itself took a while. I spent my time doing other things. That is the main step that requires more future work.
Good. All right, awesome. Thank you very much.